Welcome, ladies and gentlemen, to our lesson today. We want to look at instruction execution. I will try to make this lesson short and stick to the average time that we've been using for our lectures, where we're trying to limit our lectures to at least a maximum of 30 minutes due to the data challenges that most of you are facing in accessing and downloading the lectures. So today we will talk about instruction execution. And generally, instruction execution in computers is made up of two parts. If we are to put it in a simplified form, the first part being the fetch part, where your instruction is fetched. Then the second part being the execute part, where the processor will execute the instruction that would have been fetched. But however, you realize that this simplified version of instruction execution can be expanded further to what we term the fetch, decode, execute cycle, where we will now have 5 steps instead of the 2 steps that we find in the simplified version. So I would say the simplified version is for ordinary laymen in the street who is not familiar with computers. As for you computer network technicians, I expect you to be familiar with the 5-part instruction cycle. So when you talk about the fetch, decode, execute cycle, or the instruction execution using the fetch, decode, execute cycle, the first step will be to fetch the instruction, where the CPU will read the instruction from memory. Then it goes on to the second step, where it will then interpret the requirements of the instruction so that it determines what exactly is supposed to be done with the instruction. And chances are very high during the interpretation, the CPU or the processor will source or the instruction will indicate that there is data that needs to be fetched for the instruction to be successfully executed. So the third step will be to fetch the data that necessitates or that enables the requirements of the instruction to be successfully met or successfully executed. So once the data has been fetched that enables the instruction to be executed, we go on then to have the data processed so that we get a result. And once the data has been processed and the result has been attained, the output is then presented to the user. It's either it is written to the memory or it's displayed using the various input and output modules. So if you were doing a course called Introduction to Operating System that your colleagues who are doing software engineering are doing, we would break down these 5 steps that we've talked about into processes. So you will realize that this will now be expanded further, where probably for the fetch part, we have a list of processes that are fetching the instruction in the order in which that they are doing it. The same goes for interpreting the instruction. So we might have 5 similar processes doing fetch for different set of instructions. And I think maybe this will be a bit clearer when you look at pipelining, where we are looking at instruction pipelining. So maybe what I would advise you is to just digress a bit from your course on computer architecture and go and read about processes so that you get to understand in detail the activities that goes on when an instruction is being executed. So one of the important things during instruction execution is the need for storage space or need for storage locations where the data is temporarily stored during execution. And this storage space or storage location has to have what? Faster access times, because we can't wait for 1 second to access the data, or 3 seconds, or whatever time that is longer than necessary when what instructions are being executed. So we need high-speed storage locations or high-speed access storage locations. And the kind of storage location that is used for during instruction execution are temporary storage locations that are called registers. So as I have previously highlighted that registers, these are temporary storage locations that enable data to be quickly accessed during processing. And they make use of various pointers to store and locate data during processing. One such counter is what is the program counter. Then the other counter that they also make use of is what is the stack pointer, which is basically a pointer that addresses or that points to the current location or the current value or the last item that has been added to the stack point, or the, let's say we have 10 items stored in a stack. So the stack pointer will point to the number 10 item. That is the item that has been added to the stack or that has been pushed into the stack last. Or if the last activity that was being done on a stack is removal of an item, then the stack pointer will point to item number 9, which is the last item that is in the stack after the removal of what? Of the previous item. And we have various types of registers that are used in what? In storage of what? Of data during processing. I think we've touched about them when we did the von Neumann architecture. I want you to go back and look at them. I think we talked about the memory address register, the memory data register. So you need to relate those things to what we are talking about now. Let me also talk about the way data is arranged or stored in stacks. Basically, a stack is a storage location where we are putting items one on top of the other. If it's in a barn, we'll be putting hay bales one on top of the other. So, which means when we want to remove items from the stack, we should remove what? The item that came in what? Last. So, stack storage location uses a what? A last in, first out method. Those who did accounting, you are familiar with this term, the LIFO method. So to some extent, you can say that this is more of a disadvantage where everything has to be stored sequentially, retrieved sequentially. So it just by this characteristic, it shows probably there's need for what? For other ways of storing in and accessing data in what? In stacks. So I'll try to, or let me give it to you as a homework. I want you to go and look for alternatives or ways we can improve on the LIFO way of storing what and accessing information from stacks. That is your homework for you there. Let's look at the two operations that are performed on stacks, which are insertion and deletion of items into a stack. So when an item is being added into a stack, it's called a push operation, because we are pushing an item on top of the stack. And when an item is being removed from the stack, it's called what? A pop operation. So two operations are done on stacks, which are push and pop operations. Push, we are adding to the stack. Pop, we are what? Removing items from the stack. However, you have to understand that nothing is being physically pushed here, but this is just a way of trying to clarify the operation that are being done. Because what is basically being done is incrementing and decrementing the stack pointer. So when we push an item into the stack, we add what? SP plus 1. When we pop, we say SP minus 1. So the next item that we want to look at relates to types of stack organization. And basically, we have about 3 types of stack organizations, which are register stack, memory stack, and reverse polish notation. So this is what we're going to look at next.